Welcome you all in this talk on compact spaces, where we will see the concept of totally bounded spaces, epsilon net, sequentially compact metric space, and the relation between sequentially compact metric space and compact metric space. So, let us take suppose X is a metric space and epsilon be given number which is greater than 0. A subset A of X is called an epsilon net if A is finite and X is equal to the union of S epsilon X, where X is in A. So, in other words, you can see that if A is finite and its points are scattered through X in such a way that each point of X is distant by less than epsilon from at least one point of A. In other words, a finite set A whose elements are x1, x2, xn of X, this finite set A of X, it is called an epsilon net if every point Y in X there exists an element xi naught in A such that the distance between Y and xi naught is less than epsilon. That is to say, you can look here as an example. Suppose X is the open sphere, okay, consisting X with radius 2. Then X is the open sphere centered at the origin and radius 2. Now, if we take epsilon is equal to 3y2, then the set consisting 1, minus 1, 1, 0, 1, 1, 0, minus 1, 0, 0, 0, 1, minus 1, minus 1, minus 1, 0, minus 1, 1. That is to say, this is my X open sphere, okay, we centered at origin and radius is 2. And we have, these are the points, okay, these are the points 0, 0, okay. This is your 1, 0, minus 1, 0, 0, 1, 1, 1, and so on and so forth, and so all the points of this one. So, there are 9 points. And then you can see that if we take epsilon is equal to 3y2. So, if epsilon is equal to 3y2, so you make an open ball with center at these point and radius is 3y2. It will cover whole X. So, this is our whole X because here you take then it is because here this is 1, so we will cover up to here. So, it will cover up to here. So, it will cover like this one. Okay. So, again you take this is the center, then it will cover this portion, and now here then this will cover the rest of the portion. So, in this way, with the center at these points and we take the union of such open spheres, it will cover the whole X. And therefore, and of course, you can see that A is your finite set. So, A is finite set and the centered on each point of A and take the union, that will cover the whole X. And therefore, A is your epsilon net. But epsilon is what? 3/2. So, epsilon is 3/2 net. Now, in the suppose if we consider epsilon is equal to half, instead of taking epsilon is equal to 3/2, then what will happen? So, if epsilon is on the other hand, if epsilon is equal to 1 upon 2, then A is not an epsilon net. For example, so if X is equal to half, then what we will get? We will get this is your open sphere is this one, and then open sphere is this one, And now you will see that the point this, which is 1 over 2, 1 over 2. This point belongs to x, but the distance between y and any point and point A is greater than half. For example, if you take this point and this point, then the distance is greater than half. You take the distance, this distance is greater than half. This distance is greater than half. So the distance of this point is less than or equal to this distance is from this one. Okay, so the distance from this to this is greater than half, and therefore, or you can say that if we will make the open sphere with center at these points and radius half, then it will not cover whole x, and therefore A is not 1 over 2 epsilon net, but A, this is a 3 by 2 epsilon net. Now we have the definition of a totally bounded set. Okay, we have already studied the bounded set. Bounded set means the diameter of the set is finite. How we define the diameter? We take any 2 point. Okay, the supremum of any 2 point must be the distance between any 2 points. The supremum of distance between any 2 point must be less than or equal to some constant. So must be finite. Then the set is called bounded set. So we have studied the bounded set. Now we have the concept of totally bounded set. So totally bounded set means a metric space XD is said to be totally bounded if it has an epsilon net for each epsilon is positive. For each epsilon is greater than 0. Now you see here is we are saying that is a metric space X is totally bounded if it has an epsilon net for every epsilon is greater than 0. Now, in the previous example, we have seen that we have, suppose this is our X, but an A is equal to this one. Then this has an epsilon net. Okay, this is a 3 by 2 epsilon net, but it is not 1 over 2 epsilon net. But in the definition of totally bounded, if it has epsilon net for each epsilon, okay, so the A must be 3 by 2 epsilon net, 1 over 2 epsilon net, 1 over 3 epsilon net, and so on and so forth. Okay, and therefore we can say that here is a metric space X is said to be totally bounded if it has an epsilon net for each epsilon is greater than 0. Now let us take first let us see that what is the relation between totally bounded set and bounded set, or there is no relation, or the totally boundedness implies the boundedness, or vice versa. So let us see here is first remark is that every totally bounded metric space X is bounded, but the converse is not true in general. So every totally bounded metric space is bounded. Okay. Now since X is totally bounded, we can see that since X is totally bounded, it has an epsilon net. Okay. And epsilon net means the set A must be finite, whose elements are x1, x2, xn, and for each epsilon is greater than 0. Then we can see that X is equal to the union of all the balls as epsilon xi, and I runs from 1 to n. Okay, so take the union of this one. And now since the finite union of boundary, because this is ball, the open ball with center at xi and radius is epsilon, it is less than or equal to 2 epsilon. Okay, the diameter of this is less than 2 epsilon, and therefore it is bounded. So bounded finite union of bounded set is bounded and therefore X is bounded. So we can see here is if X is totally bounded, then it is bounded. So in general, we can say that every totally bounded metric space is bounded, but the converse is not true. That is to say, a bounded space may not be a totally bounded space. But what will happen if it is bounded? So let us say here is some other remarks. Under the usual metric dxy is equal to mod of x minus y. Okay, the real line is neither bounded nor totally bounded. So from this example, you can see that a space may be bounded, may not be bounded, may be totally bounded, may not be totally bounded. We cannot say that every space should be bounded or totally bounded. It may not be both. Okay. For example, as you have seen that here is the usual metric space is neither bounded nor totally bounded. However, a bounded subset of the real line with the usual metric is totally bounded. Under the metric d star xy is equal to minimum of mod of x minus y 1. Okay, so under this metric, the real line R is bounded but not totally bounded. So here we can see that a space can be bounded but not totally bounded. Now, an infinite set X with the discrete metric is bounded. Okay, an infinite set with the discrete metric is bounded. Why it is bounded? Because the diameter of an infinite set with discrete metric is less than or equal to 1, and therefore the diameter is finite, so the space is bounded, but it is not totally bounded. So now we have the relation between the sequentially compact metric space and totally boundedness and completeness. So the following result says that every sequentially compact metric space, okay, sequentially compact metric space means every sequence has a convergent subsequence in it. So if X is your metric space, then every sequence in X has a convergent subsequence in converging in it. Okay, so every sequentially compact metric space is totally bounded and complete. So we will prove that two things. So let us take XD be a sequentially compact metric space. Okay, and then we will prove first that it is totally bounded. So suppose that it is not totally bounded. It is not totally bounded, then by the definition of totally boundedness, that there exists an epsilon greater than 0 such that there does not exist any epsilon net. Okay, so choose a point x1 in X and form the open sphere S1 epsilon. Yani you choose an open sphere with center at this point and radius this one. Then clearly this open sphere cannot be equal to the whole space X. Otherwise, the singleton set consisting x1 would be an epsilon net for X. But here we are assuming that does not have any epsilon net. So would we have an epsilon net? So this is not true. So let x2 be an element such that x2 does not. So they are not equal. So let us take x2 an element which is not in this open sphere. Okay, but it is in X outside this one. So we have this is in outside this one. That is to say, so the distance between x1 and x2 is greater than or equal to epsilon. Now from the open sphere S epsilon x2, okay, and form the open sphere with center at this point and radius epsilon, okay, and then the union, and set the union of this open sphere and this open sphere. This is the open sphere. Then the union of two open spheres, okay, cannot be equal to the whole space. Otherwise, we will see that x1, x2, the set x1, x2 would be an epsilon net for x. So let us take here is x3, an element in x, such that x3, okay, does not lie in this union. That is to say, the distance between x1 and x3 must be greater than or equal to x epsilon, and the distance between x2 and x3 must be greater than or equal to epsilon. Now, form an open sphere as epsilon x3, okay, and is the set, okay, the set of the, and set the union of these three open spheres. That is to say, these two open sphere, one, okay, this we form two, and this is third one, okay. So this is, and again this cannot be equal to whole space, otherwise the set x1, x2, x3 would be an epsilon net. Continue in this way, what we will get? We will get a sequence xn of elements of x such that xn does not lie in the union of s epsilon xi. I runs from 1 to n minus 1, and n is equal to 2 to 3, 2, 3, 4, and so on. And therefore, you can see that from, because this does not lie, so this means that dxxn, so dxi, so dxi xn is greater than or equal to epsilon for all I runs from 1 to n minus 1, and n is equal to 2, 2, and so on, and n is not equal to I. Consequently, you will see that dxn dxm is greater than or equal to epsilon for all mn, where m is not equal to n. It means what? It means that you don't have this xn is not a Cauchy sequence, because for the Cauchy sequence this should be strictly less than epsilon. So here it is greater than or equal to epsilon. So xn, the sequence xn is a sequence with no Cauchy subsequence. Okay? If there is no Cauchy subsequence, it means that the xn cannot have any convergent subsequence. And this is contradicting to our hypothesis that x is sequentially compact, because in the sequentially compact every sequence has a convergent subsequence. So here we can see that we have a sequence which does not have any convergent subsequence. So this is the contradiction of the fact that x is sequentially compact, and hence our assumption that x is not totally bounded is not correct, and hence x is totally bounded. Now, we will prove that every sequentially compact metric space is complete. Complete means every Cauchy sequence is convergent in it. So, for that, to prove that the space X is complete, okay, for that we have to show that every Cauchy sequence converges to a point of X. Let Xn be a Cauchy sequence, okay, then we will prove that it converges to a point of X. Then, by the definition of the Cauchy sequence, for every epsilon positive, there exists a positive integer n such that dxm xn is less than epsilon whenever m is greater than n, n is greater than n. Since X is a sequentially compact space, every sequence, in particular a Cauchy sequence, has a convergent subsequence. So this sequence would have a convergent subsequence, and therefore the Cauchy sequence xn, okay, contains a convergent subsequence x kn. Okay, subsequent say k x k n. Okay, that converges to a point x in x. That is to say, the limit as n tends to infinity dx k n x is equal to 0. Now, since kn is an increasing sequence of integers, km is greater than or equal to m. So, we have the dxn x is greater than or equal to 0 by the definition of the metric, and this is less than or equal to dxn x km plus dx km x, and this is less than epsilon, and this is the same as this one. Whenever m is greater than n, n is greater than capital N. Now, taking taking m approaches to infinity, then we have when m approaches to infinity, this will approach to 0, as we have proved. Here is this is equal to 0. So, from here this term is equal to 0. So, we will get 0 is less than or equal to dx and x is less than epsilon whenever n is greater than or equal to capital N. And therefore, it means what? It means that xn converges to x. So the Cauchy sequence xn converges to a point x in capital X. So, that is to say, we can say that we have proved that every sequentially compact metric space is totally bounded and complete. But what about the converse? That is to say, every totally bounded space is sequentially compact, or every complete metric space is sequentially compact, or a totally bounded and complete metric space is sequentially compact. So, let us see here is the first example, which says that first remark says that a complete metric space may not be sequentially compact. A complete metric space may not be sequentially compact. Okay, for example, consider the metric space submetric subspace A open interval -1 to 1 of R with respect to the usual metric. Then we see that A is totally bounded but not sequentially compact. Now, here is we have another example which says that for every sequentially compact metric space may not be a complete space. Every complete metric space may not be sequentially compact. Okay, so this is not correct. So, what I do, I can take this one. So, this is not correct. So, converse is correct. Basically, I must write here is so here is actually this should be like this. Every complete metric space may not be sequentially compact. So, for example, we can consider the space CAB of all continuous real valued functions defined on the closed interval AB with the supermetric. So, we have seen in this example 2.37 that this space CAB with respect to this metric is a complete metric space, but it is not sequentially compact. Indeed, for each n natural number, we can define dn is equal to a plus b minus a 2 raised to the power minus n. Consider the piecewise linear functional f and t is equal to 1 minus 2 raised to the power n t minus a when t lies between a and dn, and the value of the function this is equal to 0 if t lies between dn and b. Then y construction f and t is continuous, and Fn Dn is equal to 0, and if m is less than n, then dfm dm is greater than or equal to half. So if m is less than n, we have d infinity Fn Fm is equal to this maximum of this one, but this is greater than or equal to this one, which is greater than or equal to half. It means what? It means that that d infinity Fn Fm is greater than or equal to m. So we can conclude that this sequence xn defined as above does not have a convergent subsequence, because this sequence does not have this sequence Fn does not have a convergent, does not have a Cauchy sequence, and therefore does not have a convergent subsequence, and hence CAB with respect to this metric d infinity is not sequentially compact. But every totally bounded metric is complete metric space. Every totally bounded complete metric space is sequentially compact. So the previous theorem holds good if every totally bounded complete metric space is sequentially compact. This is true, but if we take the totally boundedness does not imply sequentially compactness, or only completeness does not imply sequentially compactness. Okay. So here is we can prove that every totally bounded complete metric space is sequentially compact. So for that, let us take XD be a totally bounded, totally bounded and complete metric space. Then we will have to prove that it is sequentially compact. That is to say, every sequence has a convergent subsequence. So let us take Xn be any sequence in X. Okay, since X is totally bounded, it can be covered by a finite number of open spheres of radius 1. And at least one of these open spheres will contain an infinite number of members of the sequence Xn. Let n1 be a such open sphere, and let Xn1 be a subsequence of the sequence Xn in n1. Since X is covered by a finite number of open spheres and n1 is contained in X, therefore n1 can be covered by a finite number of open spheres of radius half. By the same argument, there would be an open sphere n2 of radius half, which contains a subsequence xn2 of xn1, and since n2 is a subset of n1, it follows that xn2 lies in n1. Continue in this way. For each positive integer k, we obtain an open sphere nk of radius 1 over k, which is contained in nk minus 1 and contains a subsequence xnk of xnk minus 1. Okay, that is the diameter of nk. The diameter of nk is less than 2 over k, and xnk lies in nk. Okay, where nk is greater than nk minus 1. Since xnk, xnk plus 1 all lie in nk and the diameter of nk is less than 2 upon k, it follows that d xnk plus m is less than 2 over k. So for epsilon is greater than 0, choose k is greater than 2 over epsilon, then we will see that d xnk plus m is less than epsilon. It means what? It means that x and k is a Cauchy subsequence of this sequence, and since x is complete, this will converge to a point in x. So since this subsequence converges to a point of x, so we have seen that we have considered an arbitrary sequence. Okay, we have considered an arbitrary sequence in X, and we have proved that it has a convergent subsequence, and therefore X is sequentially compact. Now, we have a corollary. We say that a closed subspace of a complete metric space is sequentially compact if and only if it is totally bounded. Okay, that is a closed subspace of a complete metric space is sequentially compact if only if it is totally bounded. Now, we have another property of totally bounded metric spaces. That is, every totally bounded metric space is separable. Okay, separable means, let me recall the definition of the separable. A metric space is separable if it has a countable dense set. Okay, so let XD be a totally bounded metric space. Then we will have to prove that it has a countable dense set. So for each epsilon, okay, because it is totally bounded, so for each n natural number, X has n 1 over n net. Okay, 1 over n net, which is denoted by an. Okay, that is to say, it has, because this is for each n, this is a 1 over n net, which is denoted by an. Now, since each an is finite, okay, because it is epsilon net, it's totally bounded, so it has an epsilon net. Epsilon net means it should be a finite set. So, each an is a finite set. Then we see that A is equal to the union of an. This set is countable. Okay, so this set A is your countable set. Okay, so this A is countable set, and now we will prove that the closure of A is equal to X. It means what? It means that if X is in X, then then we claim that X is in closure of A. That is to say, X has a countable dense set. Okay, so let X is in capital X and R is greater than 0 be given. Choose a positive integer n such that 1 over n is less than R. Let Xn consisting A1, A2, AK. Since each an is finite, then X is equal to j runs from 1 to k, X 1 over n aj. And so X lies in the open sphere with center at aj and radius half for some j runs from 1 to k. And therefore, we can see that dxaj is less than 1 over n, but 1 over n is less than r from here, so it is less than r, and thus we can see that aj lies in the open sphere with center at x and radius r, this one, and it means that the aj also lies in A. So, the intersection of this is non-empty because aj is in an and an is a subset of A. So, this intersection is non-empty. It means what? It means that at the point x, there is this for every open sphere. So, since R this is your arbitrary, so for every open sphere with radius r and center at x contains infinitely many points of A. Okay, and therefore x is a limit point of A. So, x belongs to closure of A, and hence we can see that we have considered x is in capital X and we prove that it is an element of closure of A, and therefore closure of A must be equal to the whole space X. So, we have proved that every totally bounded metric space is separable. Now, whether every separable space is totally bounded? No, it is not true. The converse of the above theorem does not hold. That is, a separable metric space may not be totally bounded. For example, consider the set of integers, which is a countable dense subset of the usual metric space R, and hence R is separable. But R with the usual metric is not totally bounded, as we have seen earlier. So, we cannot say that a separable metric space is totally bounded. But of course, as we have proved that every totally bounded metric space is separable. Now, we come to the okay, I stop over here. So, please consider this because I took pause of 5 minutes, so this would be a one lecture only. Up to here, it should be a one lecture, and khalas, finish it. Okay.